Okay, I think it's working well. So I'm recording this video for day 8 class because the coming Monday's class will be missed because of a substitute holiday in Korea. So I recorded this video and then I will post this video on YouTube. So please watch this video before day 9 class on coming Wednesday. So in the last class, we learned about memory instructions that use memory operands. So memory operand means that this type of instruction transfer data to register file from memory or memory to register file. And then that means this type of instructions handles the data in main memory. So that means these instructions access data in main memory. So that means the access the memory operands. So actually, I already explained that all type of data exist in main memory on computer systems. So in order to access this data, the data need to be transferred to the register file first, because the instructions we learned in this course just access register file, right? Like add x1, x2, x3. So that is the example of arithmetic instruction, and then this type of instruction just access data in register file. But I explained that all data handled by computer processor exist in main memory. So this data should be transferred to the register file. Also, the result of the instructions is stored in the register file also. So in order to update the data in main memory, we also transfer data in register file to the, the data space in main memory. Okay, so I explained that there are two types of instructions, the load instructions and store instructions. So actually, there are only two types of instructions. It's a memory instruction. So load instruction just transfer data from memory into registers, and then store instruction, there's a reverse direction. So that means store instruction transfers data from register to main memory. Also, memory is byte addressed, so this is so important. So that means that the unit of address number 1 is byte. So 1 byte just refer is the memory space that has the size of byte. That means 8-bit. And then RISC-V applies the literal endian addressing. So I also explained about the literal endian here. So if the data size is larger than a byte, a single byte, then the RISC-V part, that means the lower part of the data is stored in the memory space that has a smaller address number. So that means the literal endian memory system. So the most of the computer systems apply literal endian memory system. Okay. So RISC-V does not require word to be aligned. So one of the students posed a question about this unaligned memory addressing in RISC-V. So I also posted the answer for this question. So please refer the answer for this RISC-V unaligned addressing. Okay. So this is example, and then register and memory. So in the previous class, we learned the instructions that access register file. So why do we need register file? So I explained that the register file is the small memory space. That means that the data, so data is stored in this small sized memory space. It's actually the storage space. And then for instructions of computer processor, the data is accessed from this small register file. Why? Because smaller is faster. Okay. The size of the register file is much smaller than the size of the main memory. So actually the main memory size is very large, and recently we frequently use the 4 GB of the main memory or 6 GB or 8 GB. So there is some commonly used memory size in our smartphone or laptop or desktop computers. But compared to this large main memory, so the processor just the RISC-V processor just handles 32 general 32 and 64-bit width general purpose registers. So the size is very small. Then the speed is much faster than the main memory because smaller is faster. Okay. That's why the computer processor just frequent the computer applications transfer the frequently used data into register file by compiler. So compiler just manages these general purpose registers in applications. So, and then this data is frequently accessed. So very quickly. So for the higher performance, okay, because the small memory is faster. Okay, also we learned about the immediate operand. So immediate operand means that it's the constant value. So, and then, but the size of this value is the magnitude, that means the size. The magnitude of this constant value is small. It is because, you know, in applications, we frequently use small constant numbers like I equal I plus 1 or I equal I plus 2. So that we frequently handles this small constant number. So if this small constant number can be stored in an instruction, then we don't need to make a memory space for this small constant number. Also, we don't need to transfer this data from main memory to register file. So because this constant data can be included in the instruction. Okay, so we will learn how the instructions are translated from the assembly code or assembly instruction. So, but you will learn that how this constant number, so that means the immediate data can be included in the instruction. Okay, so I already explained the benefit of this immediate operands. So computer instructions can also handle these immediate operands. Okay. And signed, and we also learned about the signed and unsigned number. So if we handle the number system, so we need to consider if the number is signed numbers or unsigned number, because in the signed number, the MSB it represent signed bit. So that means if MS bit is 1, that means this number is negative number. And if not, that means this number is positive number. So why is it important? Because this information is used for sign extension. Okay, because sometimes the size of data, that means the width of the data can be different for some different variables. So For example, for the add instruction, one operand can be byte, while the other operand can be word. So that means the width of these two operands are different. So for this operation, we need to extend the bits of the byte data. Okay, and then for this bit extension, we need the information about the signed or unsigned value for this byte data. Okay, sign extension. Okay, so we briefly covered how the instructions are represented as the machine code in the previous class. So I explained that RISC-V instructions have several instruction types, such as Rtype, I-type, S-type, or U-type. So there are many instructions for RISC-V ISA. So, but we group the several instructions, and then this group of instruction can have the same format. Also, we learned that in the instruction, there are different fields, such as this is the instruction. This part represent an instruction, and then this part represent target register file, and then this part represents source register file and another source register file. So machine code instruction is a machine instruction need to include these information, like the operand, op code. So operate, that means which operation is used, and then the number of target registers, and then also the number of source registers. So these all information should be included in this machine code instruction. Okay, the machine instruction. So also we learned that the size of a single RISC-V instruction is 32 byte. So that means 32 bits. So that means there are 32 bits that can represent a single instruction in RISC-V ISA. Okay, and then we also categorize these instructions as R-type, I-type, S-type, and U-type. So we will learn how the instruction can be represented in detail in today's class. Okay, let's move on. Okay, so this is the R-type instructions. This is also okay. As I posted this Excel file. So this Excel file summarizes some RISC-V into focus that this is IV32I. So it's a little bit different because the register file size is 32-bit, but in this course we will learn we are learning about IV64I. That means that the register, a single register width is 64-bit, but it's the instruction structure or instruction type is very similar between IV32I and IV64I. Okay, so I summarized this a category of instructions such as load, store, shift, and arithmetic instructions. Also, you can find the format of instructions here. You can find the description of each instruction. Also, you can find the OP code and then function 3 field and then function 7 field of instruction. Okay. So please find this file in the resource tab of Piazza. Okay, let's go back to the slide. So let's learn about the R-type instruction. This R format instruction, or it's called the R-type instruction. So this type instruction, the example of R-type instruction is add instruction. Add x1, Okay, let's see. Add RD is the destination register, RS1, source register 1, and RS2. So I already explained that this information should be included in this machine code instruction. So as you can see, this RD is here, and then we already learned that the RISC-V has 32 general purpose instructions. So we can represent these 32 general purpose register number, so 32 general purpose registers. Okay, so we can represent these 32 general purpose registers with 5-bit unsigned number, right? Because there are 32 registers. Okay, so RD is here. RD field is here. So, and then 5 bits are assigned for this RD field. And the RS1, how about the RS1? RS1 is here. And RS2 is here. RS1 and RS2 also have 5 bits width because there are 32 general purpose registers. And then in order to represent the add instruction, we need to use the 7-bit opcode field, and then also 7-bit additional function 3 field, and then also 3-bit function 3 field, also 7-bit function 7 fields. So let's see how can we represent this add instruction. So actually RD, the destination register number, and then source register can be easily represented with the register number. Then how can we decide the opcode in function 3 and then function 7? Okay, let's see the Excel file here. So as you can see this Excel file, you can find the add instruction here. So add, so you can find the exemplar add format here in the Rtype. And then if you see this row for add instruction, you can find the opcode field here, and then function 3 here, and function 7 here. So what does that mean? So in order to represent the add instruction as machine code, the opcode field should be 0110011. Okay, and then function 3 is 000, and then function 7 field should be all zeros. Okay, so for this add instruction, there are. So this is the example of alphabet instructions like add x9, x20, x21. This is RD, RS1, and RS2. So as you can see, RD is here, RS1 is here, and then RS2 is here. So you can find the 9, 20, and 21. That's the register numbers. And how about the add instruction? So we can find that the opcode for add instruction is 0110011 in the Excel file. So it's here. And then also function 3 field is a 000. And then function 7 fields are also all zeros. So by combining these information, we can generate the instruction machine code instruction for this add x1, x20, x21. Okay, like with the binary number, we can represent this instruction like this, and then with the hexadecimal number, then we can represent this instruction like this. So we frequently use hexadecimal number to save the reduce the width of the binary number. Okay, because in order to represent the machine code with the binary number, then we need the 32 digits, but with the hexadecimal number, we just need the 8 digits. Okay, and then let's see the I format instructions. So In this Excel file, you can find several I format instructions. So for example, load instructions have also I formats, and then as you can see, some instructions, some arithmetic instructions such as add I also has I formats. Also several shift instructions such as SSLI, SRLI, so has also I format instructions. So for several logical instructions have also I format instructions. So you can find several I format instructions. Then let's see how immediate fields are represented with the machine code instruction. So what is the what is a feature of I format instruction? One of source register number is replaced to immediate number, immediate operands, right? So I format instruction just require one destination register and one source register and one immediate operand. So the R format instruction, we need one destination register and two source registers, okay? But unlike these R format instruction, the I format instructions have one RD and one RS1 and one immediate number. So immediate number is the constant number and it's 2's complement number. So that means the MSB of this immediate number is sign bit because it's 2's complement number. And then in a RISC-V instruction, immediate number has 32 bits. Okay, immediate number occupy 32 bits of a single RISC-V instruction. So what is different? Compared to the alphabet instruction, so OP code field is the same. So like here, RD is here, so 5-bit here. Then function 3 field also is same. RS1 is here. And then in the alphabet instruction, this part was function 7 field and RS2 field. So these two fields are merged and becomes immediate field, immediate number field, okay? In the I format instruction. And then for the immediate number, so we can use the 32-bit signed number, okay? It's signed. Okay, so let's see the example of the, so for this I format instructions, RISC-V, we use the load instruction. So load instruction is also I format instructions. Also several shift arithmetic and logical instructions and compare instructions also have I format instructions. So as you can see, we can find the OP code for the load type instruction. And also we can find the OP code for shift arithmetic, logical, and compare instructions. So actually for the I type, shift arithmetic, logical, compare instructions have same OP code like here, 001, 0011. And then load instruction has load instructions have different OP code like 000011 like here. And then we can find also the different function 3 field here and then function 7 field here, okay? Okay. So, okay, here. So how can you represent add I, x1, x2, and 4? So in this example, we need to represent the add I instruction. with the OP code and function 3 fields. And then this is a destination register, so 1. And then source register number is 2. And then immediate value is 4. So we can just assign the 4 here, 2 here, and then x1 here, so RD. And for the add I, so here, so for the add I, the OP code is 001, 0011, and then function 3 is 000, and then no function 7 field because immediate format does not have function 7 field. So we can just zero zero one 0011 for this OP code field, and then function 7, function 3 field has all zeros. Okay, that's it. So if we compare this Rtype formats and I-type formats, so you can find that same fields like OP code fields or RD fields, function 3, RS1, these common fields share the same location of instruction. So if we just see the lower 20 bits of R-type format and I-type format, so these fields are the structure of these fields is the same. Okay, but which part is different? We just are this higher bit parts like MSB parts are different like functions. So what can I find for these some common fields for different instruction formats? So even though the formats of the instructions are different, but the same fields are located at the same location of instruction. So that means by doing this, we can simplify the structure of instruction decoder. That is the hardware. Okay, so we can use the simpler hardware because the different instruction formats share some same field location or some same field number of the same field width. Okay. And the S format. So in the S format means the store type instructions. So if you see this Excel file, okay, so you can find there are several store instructions. So please note that this is IV32I instructions. So and then you can see, oh, this is store S type S format instructions. Okay, so what is different? So okay, we learned that there are two types of instruction like the loading. Oops. So loading. Oh, what happened? Okay. So load instruction, load x1, offset is here, and then store double word x1 for x2. So we learned that there are two types of memory instructions in the RISC-V ISR. So we can compare the load instruction and then store instruction. So we learned that load instruction is the I format instruction, but store instruction is the S format instruction. So what is different? But if we see the S format instructions here, so you can find that there are two source registers, RS1, RS2 here, and then there is no destination register file. So instead of RD field, the part of immediate field fills this 5 bits RD field of the I format instructions. Right. Why? So let's see the meaning of this load instruction and store instruction. Okay. So in the load instruction, we just move data from memory to register file. So that means the transport data is written to the register file. So this X1 becomes the destination register file. How about the store instruction? In the store instruction, we just read the data from the register file, and then this read data to move this RISC-V processor moves this data to memory, the main memory. So actually, this register number is the source register number. And then in order to calculate the target address of a load and store instruction, we need to also read the base address from a source register, like X2 here. So load instruction has one destination register and one source register, but the store instruction has one destination, one source, two source registers, like here. So that's why store instruction has RS1 and RS2. And then as we learned, the RS1 field is located here and RS2 is located here. And then there is no RD field. So the immediate field is split, and then some part is stored in the higher 7-bit location of a RISC-V instruction. And then the lower part is stored in this 5-bit lower lower part of the instruction. Okay. And then, but except this one, it's the same. Okay. So as you can see, for the S type, the opcode field is the same. RS2 and RS1 is the same to the RS1 and RS2 of the R-type instructions. And then there is no RD, so immediate value is split, and then higher part is located here, and then lower part is located here. That's it. Okay, we learn. Oh, it's not saved. What happened? Okay, saved. Okay. Now let's see how instructions are stored in the computer systems. So we learned that instructions can be also represented with the binary codes or binary numbers. Also, computer systems handles only the binary number, so binary data. What does that mean? If we see on instruction, so it's a machine instruction, this format means the machine instructions are also represented using binary number. Also, the data handled by these instructions can be also represented using binary numbers. So if we see instructions, so this format of instructions are the same to the format of binary data. That means it's a normal data actually, because computer systems can only understand the binary numbers. Okay. So instructions are represented in binary here, just like data. So instructions are also stored in a memory like data, binary data. So instructions and data stored in memory. So what does that mean? So here is the processor, and then this is the main memory. And then in order to execute these instructions, the instructions stored in the main memory should be also transferred to the processor. So processor here. Also, instructions are stored in the main memory. So that means in order to access these instructions in main memory, we need addresses. Right. So here is the memory, and then some data is stored in the memory. And then in order to point the location of the data, so in order to access the data is in main memory, so or actually all type of memory, we need to know the address of target data. And then I also said instructions are stored in main memory like other normal data. So that means in order to access and then in order to execute these instructions are also transferred to the processor. Okay, that means in order to access these instructions, we need addresses for these instructions. Okay, that we need to access the instructions. So address informations are also required, and then these addresses of instructions are called program counters. In abbreviation form, it's called PC. It's a program counter. Okay. This is because instructions are stored in main memory like normal data. Then in order to access this instruction, we need the addresses for instructions. And then we call these addresses for instructions as program counters. Okay. So actually the all type of data are stored in main memory like this figure. Okay. So you need to remember that PC is an address of a instruction. It's very important. Okay. So let's learn about the other logical instructions. So sometimes we use the logical instructions such as shift left or shift right or bitwise and, bitwise or, bitwise exclusive or instructions. So if you see the C or Java operators, you can find the shift operators such as like this. And then also we can find that bitwise and operators and the or operators and exclusive or operators. So in order to support this type of operators, RISC-V has also shift instructions and logical instructions. Okay. If you see this Excel file, you can find that several shift instructions here. Also, you can find that several logical instructions here. Okay. So this is the instruction format of shift instructions. So you can find that it's the format of this instruction is a little bit different from immediate type instructions. Okay. So in the this is the typical I format instructions like add I. So we can find that the opcode field here, 7-bit opcode field here, RD is here, function 3 is here, RS1, 5-bit RS1, and then there is 12 bits of immediate field. But if we see shift instructions, we can find that So what is different? There is function 6 field or function it's a little bit different. So in the Rtype instruction, there is function 7 field, and then immediate 6 bit of immediate field here, rs1, rs and function 3 rt is here, opcode is here. So this part is different from I format instructions. And so if you see the Excel file here, then you can find that in the shift instructions, there are normal instructions. There is the R-type instructions here, the SLL, and then there are I-type instructions like SLLI. So you can find that, oh, this is the immediate value. But this immediate I-type shift instructions are a little bit different. So that means the format of these instructions. Okay. So if we use the normal R-type instruction like X1, X2, X3, so that means that this is the X1 is X2, shift to left, X3. So if we perform the shift to left, that means that we just move the bits to the left by number of this register data. So we just fill the 0 to the rightmost part of the data, and then we just move the all data to the left, and then shift to right is different. We just move the data to the right, and then we can fill the rightmost part as the 0. This is the SRL, shift to right logical. And then if we use the SRA, A means the arithmetic, we just fills the rightmost part as the MSB. That means the sign bit. So there are 3 types of shift instructions like SLL. So SLL means just the shift left, and then we can fill the rightmost part using 0, 0, and then SRL, the shift right logical, we just move the data to the right, and then we fill the rightmost part using 0, and then SRA is the shift right arithmetic. So that means it's the shift right, and then we fill the rightmost part using MSB, the sign bit. And then so the format of the shift instruction is a little bit different because this is RV64I. So in the Excel file, I just shows the, where is the, okay. So in the Excel file, I just summarized the IV32I. It's a little bit different. I think it's not shared. So, okay. Sorry. There are 3 types of shifting operations, like SLL, SRL, and SRA. So, and then let's what is different between IV32I and IV64I. So if you read the ISA manual of RISC-V, then you can find that this is the IV64I base integer instruction set. So actually the basic instruction set is the IV32I. The common parts are the same, but some parts are a little bit different. So if you see the IV64I base integer instruction set, then you can find that, oh, this is the shift instructions. So in the IV64I, there are 2 types of shift instructions, like normal shift instructions and word shift instructions. It's a shift instructions for 32-bit data like SLLIW, SRLIW, and SRAIW. So if we just focus on the 64 shift immediate instructions for 64-bit data, the double word data, you can find that the bit width of the immediate number is 6 bits, but for the 32-bit data, it's 5 bits. Okay, it's because of the size of the bits. Okay, if we just handle the 64-bit data, we require the 64-bit immediate value for shift instructions, right? It's obvious, right? Because it's a 64-bit data. So we need 6 bits of immediate value for shift instructions. But for the 32-bit data, we just need the 5-bit immediate value for shift instructions, right? Understand? It's obvious. And then also, I think this slide was not shared. So there are 3 types of shift instructions, like logical, shift left logical is a SLL, and then shift right logical, SRL, and shift right arithmetic, SRA. So what is different? In the shift left logical, we just move the entire data to the left side. So, and then if we, so for example, 0, 0, 0, 1, and then shift left 1 is the 0, 0, 1. Now, how can you fill this part? We fill this part with zeros, okay? So that means, so SLL by 1 is equal to the multiplied by 2 in the binary data, right? And SRL, we just move the data to the right side, and then we also fill this MSB, is the rightmost part using 0. So that means the SRL, so shift right logical, and then SRA, shift right arithmetic. We just fill this rightmost part using MSB bit of original data, okay? Because this bit is signed bit, okay? So shift right is similar to divide by power of 2, because this is binary data. Like, so if the original data is 0, 0, 1, 0, and then shift right, if we use the shift right logical, is a SRL, then becomes the 0, 0, 0, 1. Because so 2, it's 4. So divide by 2. Okay. And other part. And operation. So and instruction just performs bitwise AND operation. So bitwise AND operation means that bit by bit AND. Okay, that's it. Or or instruction also means bit by bit or operation. It's a bitwise or operation, like here. So bit by bit or 1, 1, 1, 1, 1, and so bitwise AND operation becomes, so it's a 0, 0. Result is 0, 0, 1, 1. Okay, I think it's just bitwise or operation, and the exclusive or also means bitwise exclusive or operation here. Okay. This slide also shows the summarized instructions for RISC-V instructions. So like this Excel file, oh, I need to share. Like this Excel file, this slide also shows the list of summarized instructions in RISC-V. Also, I copied this table from the textbook. Okay, So please read the textbook. Okay. So as you can see, there is arithmetic. There are arithmetic instructions. There are data transfer like load and store instructions and logical instructions, shift instructions, conditional branch. So we'll learn about the conditional branch today. Unconditional branch like jump instructions here. Okay. So you can find the big code and the function 3 and then function 6 or function 7 field of the these instructions. So if we know the format of instructions, and so if we know the object code and function 3 and function 7 field of instructions, then we can translate the assembly instruction into machine instructions, right? Easy. Okay, there are several type of instruction like here. Okay, let's learn about conditional branch or branch instructions. So these are instructions for making decision. So what does that mean? Making decision. So we frequently use the conditional statement. That means if A equal 1, then do something. Else do another thing. So this is the frequently used conditional statement of C code. Well, and then these type of statements are frequently observed in normal applications, right? So if there is no conditional statement in the high-level language, then our application should be very should be dumb. So that means there is no conditional instructions here. But because of these conditional statement, we can write some smart code for the condition of variables. Okay, like if A is 1, then do something, and then else, if A is not 1, do another things. Okay, like this. And then computer instructions also need to support this type of instruction statement. So let's run. So let's learn about conditional branch. So if we see the conditional statement, then conditional statement, then we can find that the execution path of this code is divided, is split into two parts. What does that mean? So based on this condition, so true or false based on the condition, then this application do something and then do another thing. So execution path is split into two parts. And then after this conditional statement, and then the flow of the execution is merged. So based on the if execution path is divided, that's why these instructions are called branch instructions. Like it's a tree, and then the branch is divided from the main root of the tree. So that's why these are called the branch instructions. And then so we will learn about the conditional branch instructions. So in order to support the if condition, then do something else to A and B, to B. This is the condition. So The the RISC-V also supports this type of operations. So let's see how can we implement this statement. If condition, then A as B. So I said that the execution path is divided like A part and B part. And then in the previous slide, I explained that instructions are also stored in the main memory, like here. So that means the A part is stored in some place of memory, and then B part is stored in the another place of memory. Okay, so what does that mean? Based on the condition, so as a condition, the computer processor can execute the A part, or is it true? Okay, it's true and it's false. So that means, oops. The program is messy. I don't know. So it's a false and it's true. Okay. If the condition is false, then A is executed. It's a false. And then if a condition is true, then let us assume B is executed. Then I said the A part, the code instructions for A part is stored in the memory. And then instructions for B part are also stored in the memory. That means I also explained that the location of the memory can be represented with address, and then this address is called program counter. So how can we divide the execution path? We can distinguish the execution path using program counter. So if the condition is false, then we just set PC is for A part, and then if a condition is true, and then we just set PC for address of instructions B. That's it. So this conditional branch instruction or branch instruction just changes or just manipulate program counter of executed instructions. Okay, that's very important. Branch instructions or conditional branch instructions, like the branch means just jump instruction. Conditional branch instruction is branch or if something. These instructions, branch instructions, just changes the program counter of executed instructions. Okay. Okay. So let's see the example. It's a BQ RS1 and RS2. It's a two source registers. This is the BEQ. That means the branch if equal BEQ. Okay. So this BQ instructions that there are two source registers, read the data from the two source registers, and then if the data in these two source registers are the same, just compare the data, then jump to L1. L1 means the PC of target B, because if condition is true, okay? So BQ means that if RS1 equal RS2, then PC becomes L1. That is the meaning of BEQ. Then if the condition is false, then PC is the PC plus 4. So that is the next instruction will be executed. So if the condition is true, the instructions pointed by target L1, this is label 1, label 1 will be executed. And if not, then that means the condition is not true, so false, then the next instruction will be executed. So what is the next instruction? So I said that the size of a single RISC-V instruction is 4 byte, and then address is byte address in RISC-V processors. So the PC of the next instruction is PC plus 4. Okay, so this is the instruction A, instruction B, instruction C. So it's the next instruction is B. So this is the address for this A is it's a lower A. Then the address for this next instruction B is the A plus 4. Another next instruction is the A plus 8. Okay, because the size of a single instruction is 4 byte. Okay, so you need to understand that this is a very important concept in the programming. The conditional branch instruction. Also, you need to also understand the meaning of program counter. Okay. If you have any question, post your questions on Piazza. And then BNE RS1, RS2. So that means that it's the branch if not equal NE. So that means if RS1 is not equal to RS2, then jump to N1. So just condition is different, but the meaning is similar. Okay. So these are postfix of the branches, conditional branch instruction. The postfix just change the condition of comparison. Okay, just to read the data from the two source registers, and then we just compare these two data, and then if the condition is true, and then jump to L1, and if the condition is false, and then just execute the next instruction. That is the meaning of conditional branch instruction. Okay, let's see the Excel file also. So if you can find the branch instructions, and there are several different type of branch instructions here, like BQ, PNE, PLT, PG here, and then you can find the meaning of the branch here. Okay, so and the branch instructions also have SP type. So it's a little bit different. It's similar to S type instructions, but the format is a little bit different. Okay. So this is the example code of the conditional statement in C. If the I equals J, and then F equals G plus H, and then else, if not true, then F equals G minus H. And these variables are stored in register file X19, X20, and blah, 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 blah. So this is the compiled RISC-V code. So we use the BNE. So that means if, and then I is here and J is in X23. So we just compare the I and J. And then if true, and then go to the else. So if I equals J, so we use the B and E, that means not equal. So then if I equals J, that means the condition is false. If condition is false, if I equals J, so do not be confused, then F equals G plus H. Then we need to use add instruction. Okay. So it just the very next instruction is executed. And then if the condition is true, then go to the else part here. Like sub, we use the sub instructions. But if you see this if else statement, then after this else statement, then the execution path is also merged. So this execution path is divided to the F equals G plus H. Also, the execution path is divided into F equals G minus H based on the condition of I and J's. But after this statement, the execution path is merged. So how can we merge the execution path? So after this add instruction, jump to the exit here. And then after this sub instruction, so just the next instruction is executed. So naturally, this exit, the instructions labeled by exit is also executed after the sub instruction. Okay, so based on this if instruction, we need also unconditional branch instructions. But we can use the jump instruction. But in this example, we just use the BQ and we use the X0 as source registers. So we just compare the 0 and 0. It's always true. Then jump to exit. That's it. Okay? Understand? So try to understand this example. So this is another example of branch instructions from the loop code. So we frequently also use the loop statement like for loop or while loop. So in this code, we just compare the data in save I indexed by I to K, and then if this condition is true, I equal I plus 1. Okay. So I is in X22 and the K is in X24, and then the base address of a save array is in X25. Okay. So in order to represent the save I, and then there's also the size of the variables, so actually each element of this save array, and then size of each variables is double word. So that means the 8 byte. Okay. So in order to represent the save I, so we need to use the base address of save plus 8 multiplied by I. Sorry. So base of save plus 8 multiplied by I. So in order to represent this, so we calculate the I is here, and then shift left 3, that means the I multiplied by 8. So this is this code, and then just add this I multiplied by 8 to base address of save. Okay, right? So just to access the save I here, and then data of save I, store data of save I into X9. And then we just compare the X9 and K. Right, K is in X24. If not equal, and then escape the loop here. So go to the, if not equal, then go to exit. Okay. And then if equal, then just equal I plus 1. And then go back to the start of the loop. Okay, understand? So that this while loop can be translated into RISC-V assembly codes like this. Okay. Okay. And then okay, I will complete the today's class with the basic block. So the basic block, so we learned about the branch instruction. So that means that the execution path can be changed by branch instructions. So now we will learn about the concept of the basic blocks. So basic blocks means that basic blocks means if an instruction of a basic block is executed, then inside of the basic block, the instructions can be executed sequentially inside of the basic block. So that means in a basic block, instructions are the instruction execution path is single. So only one instruction execution path. Okay. So this is the definition of a basic block. A basic block is a sequence of instructions with no embedded branch except at end. So that means that in the basic block, the branch instruction like B, Q, or like jump instructions can be only at the end of the at the last instruction in the basic block. Okay, so inside of the basic block, except the last instruction, if there is a branch instructions, there is a branch instruction, then this block cannot be basic block. So no embedded branches. So branch instruction can be only at the end of basic block, and then no branch targets. So except at the beginning. So in the basic block, the branch target can be only the first instruction of the basic block. So that means in the basic block, if this instruction is executed, so instructions are executed sequentially in one single path. Okay, because there is no branch instruction inside of basic block except the end of basic block and the last instruction. Okay, so we can guarantee that if this instruction is executed, and then the instructions inside of this basic block is executed sequentially without any branch. So if the instructions are executed sequentially, then the efficiency of the computer processor will be very high. But if the instructions include some branch instruction, then the execution path is divided, so the efficiency is decreased. So basic block is actually very important and very critical for the performance of applications. Okay. So in order to understand the performance by basic block or some branch instructions, we need to understand how branches instructions are executed in the real computer processor hardware. So we learn about this in the chapter 4. Okay. So, but please to remember the definition of basic blocks. Okay, it's very important because some compiler optimization is performed based on the structure of basic block. Okay, then there are several conditional instructions like BLT, BG, and the RISC-V. So as you can see, if you know about the additional branch instructions, then please see this Excel file. Okay. Okay. Also, sometimes if we sometimes we need to compare the magnitude of two two data stored in the register files. Like, and also if we use the BLT or BG, so then BLT means the branch if less than. So it's a BLT, branch if less than, or we can use the BGE, branch if greater or equal. Okay, but in order to compare the two numbers, then we need to consider the also signed number or unsigned number. Okay, so if we just compare the unsigned number, we need to use the BLTU or BGU, right? Or then if we just compare the signed numbers, then we can use normal BLT or BGE. Okay, like this. So for the signed comparison, we can use the BLT and BG, and the unsigned comparison, we can use the BLTU and BGU. Like here, it's unsigned. So you can find here. So you can BLTU and BGU. Okay. It's unsigned and unsigned. Then for the signed numbers, we need to use the BLT and BGE. Okay. Okay. So I will stop here. So this is the end of day 8 class. And then please watch this video before day 9 class, which will be on Wednesday. Okay. Okay. Thank you for your attention, and thank you for watching this video. And then please enjoy long weekends. Okay. Bye.